Alright, so in this one we're going to look at some story problems. They're really just story problems, you just have to do them. There's no nice, easy way. You can see examples of them done. So read through the section and you follow them. So here's the first three. I'm going to do 7, 8, and 9. And this is about the logistics model. Alright, so they give us the function f of x is equal to 150 over 1 plus 8 e to the minus 2x. Now the logistics model has a graph that looks something like this. At time 0 is where you start, and then over some time period you have this horizontal asymptote, right? It's going to go up, and then it's going to change. Now this is y equals c, and that's called the carrying capacity. Now, if your population or whatever starts above it, that's going to come down to that. But anything below is going to grow. And the spot here where it changes from being turning up to turning down like this, that's called an inflection point. That occurs at c over 2, like this, at halfway in that spot. Now, the carrying capacity is the long-term behavior. What happens as you go off to infinity? Well, notice that what's going to happen is that this term right here, as you put in bigger and bigger in x's, this is going to get smaller and smaller. So this thing's going to go to 0. So it ends up that our carrying capacity, which is c for this example, is 150. So that's the answer to 7. Or actually, that's the answer to 9. Number 7 is just interpret f of 0. So if I plug in 0, I would get 150 over 1 plus 8 e to the minus 2 times 0, which is just 150 over 9. So this would be the starting population or the starting value, whatever that is. So this, let's see, that would, if I plug this into my calculator, I get 16.6 repeating. So whatever this population that we're concerning ourselves with, this would be the starting place. Whatever this value is right here, that would be 16.6 repeat. 6 2/3. 16 2/3, I mean. Now number 8 for this problem, f of 4, that would be just after whatever 4 units of time. Usually this is time, right, and population. So this would be like 4 days or 4 months or 4 years or 4 whatever the time units that an integer is down here. So that would just be f of 4, which is 150 over 1 plus e to the minus 2 times 4. And again, we can plug that into our calculator. And we get 149.949, like that. So whatever this population is related to, rabbits, whatever, something, we know that we'd start off with, maybe it's thousands or millions or who knows. And then this is our starting place. So it's going to grow from 16. It's going to go through 149 at 4. So that means it's almost up here. So by the time we get to 1, 2, 3, 4, we're right here at 149.949, and if the carrying capacity is 150, we're right below it. So, alright, so let's do number 36. A wooden artifact from an archaeological dig contains 60% of the carbon-14 that is present in living trees. So currently, 60% of the carbon-14. To the nearest year, about how many years old is the artifact? And it gives us the half-life of carbon-14 is 5,730 years. Alright, so we're going to use exponential decay, which is this function right here. Now what I'm going to do is I want to figure out k. So what does half-life mean? Half-life means the amount of time until you get half of what you started with. So half of what I started with would be half of A naught, whatever that is. We don't even know. Those divide out. Oh, and this has to be the 5,730. So I get half is equal to e to the minus k times 5,730. Now I take the natural log of both sides, and I get ln of e to the minus k times 5,730, which, since these are inverses, just minus 5,730k. Divide that over, so I get k is equal to 1/2 k is equal to the ln of 1/2 divided minus 5,730. So k is equal to, we can do this on our calculator, and we get negative 0.000121. I'll round it off. Now we can take that, go back, and use this information. So 60% of what I started with would be 0.6 times A naught. Plug in my k, which would be minus 0.000121 t. The A naughts divide out, and so I'm left with 0.6 equals e to the minus 0.000121 t. Take the natural log of both sides because I want this down in front. So I have the ln of 0.6 is equal to ln e to the minus 0.000121 t. These are inverses, so that means this is minus 0.00121 t. This is natural log of 6 still. Divide that over, so what I get is t is equal to natural log 1.16 over negative 0.00121. I plug that in the calculator, and I get 4,222 when I round it off to the nearest year. Alright, so this one, let's try the Newton's law of cooling here. So for the following scenario, they take a pot of soup off with an internal temperature of 100. So that's our initial temperature of the object, is 100 degrees Fahrenheit. Set off in a room, so our surroundings is 69 degrees Fahrenheit. Taken off the stove and let cool in a room, 69 degrees. After 15 minutes, the internal temperature is 95 degrees. So T of 15 minutes later, is 95 degrees. Now, Newton's law of cooling is T of temperature time A e to the minus kt plus Ts, where that's the surrounding. And A is equal to the internal temperature minus the temperature of the surroundings, like that. So A we could calculate right away. That's 100 minus 69. So that would be 131 degrees, or 31. And then Ts, of course, is given. So I have T of T is equal to 31 e to the minus kt plus 69. So at time 0, this is a 1 and adds up to 100. So all's good there. Now, to get the k, that's where this piece comes in. So I need to plug in T of 15, which is 95 degrees. But that's also 31 e to the minus k times 15 plus 69. So now I solve for k. So I subtract this over, so that's 95 minus 69. Divide it by 31. And I get e to the minus 15k. Alright. Take the natural log of both sides. I could figure this out, but I'm going to make the calculator do it anyway. And then those are inverses, so then I can just write it as minus 15k. Divide the 15 over, so I get k is equal to the ln of 95 minus 69 all over 31 divided by negative 15. So now I go to the calculator. So I get that K is approximately 0.011726. So maybe I'll round it off to 0.01173, like that. Just so we have a bunch of digits there. All right, so let's see what what we're trying to do here is use Newton's law of cooling to write down a formula. Well, we did that, or almost done with that. We have T of T is equal to 31 e to the minus 0.01173 T plus 69. So there's our formula for our Newton's law of cooling. Now 41 says the nearest minute, how long will it take to cool to 80 degrees? So I take my formula that I have, T is equal to 31 e to the minus 0.01173 T plus 69, and I set it equal to the 80 degrees, and I solve for T. So I subtract over the 69, so I get 80 minus 69, divide by the 31, 1173T is equal to 80 minus 69 divided by 31. Take the natural log of both sides. And so this thing, since they're inverses, I just get that. 0.01173T is equal to the ln of 80 minus 69 over 31. And then I divide this over, so I get T is equal to ln 80 minus 69 over 31 divided by minus 0.01173. Now I plug that in my calculator, and I get 88.328 minutes. So to guarantee, right, so we'd probably just say 89 minutes to make sure that it's actually the temperature that we want. Now the last question is, to the nearest degree, what temperature after 2.5 hours? So we have T is equal to 31 e to the minus 0.01173 T plus 69. 2.5 hours is, well, multiply that by 60, right? Because we're in minutes. We did this in minutes. So this would be 2 times 60 is 120, plus 2 times a half is 30. So that's 150 minutes. So I'm going to put in 150. This would be 31 e to the minus 0.01173 T plus 69, or sorry, not T, but 150. And again, this is just plug it in the calculator. And it looks like we get 74.3 degrees Fahrenheit.